Why does it seem so much easier for things to fall apart than to stay organized? Sandcastles don't last for long. The particles start to spread out, and our beautiful castle loses its form. The sand's tendency to disperse reflects a fundamental idea in chemistry: entropy. Entropy tends to increase, and that increase can drive chemical processes. But how do we use entropy to help predict the spontaneous direction of a chemical process? Let's uncover the surprising power of entropy. This is Real Chem. You may have heard entropy described in terms of disorder. However, that's vague, and if taken too literally, it can be misleading. But entropy itself isn't vague. It has a precise mathematical definition, and changes in entropy can be measured with precision. The mathematical definition of entropy not only gives us precision, it helps us build intuition. With it, we can predict whether a process will increase or decrease in entropy. Since entropy is one of two fundamental driving forces in chemistry alongside energy, understanding it is key to predicting how processes unfold. There is a mathematical precise definition of entropy. S is equal to R natural log omega. R is the constant that appears in the ideal gas law, PV equals nRT. It's just a number. The interesting part is omega. We can say that this is the number of different possibilities for a system to arrange itself. It can be difficult to calculate precise values for omega, but we can use our intuition to estimate how the number of possibilities changes as the systems change. Let's look first at phase transitions. If we look at this transition of a solid to a liquid to a gas, the solid is highly organized. Every atom has a specific spot in the crystal, and the atoms don't move out of their spot. Like when you have a classroom with 24 students and 24 desks, everything is in a row and a column. As long as everyone stays put, there's only one possible arrangement. So omega equals 1. But if we move to a liquid phase, this would be like having those students in a lab where everyone is still in the same vicinity of each other, but they can move from one spot to another within the room. Now there are so many more possibilities for how everyone can be arranged. The omega for this more fluid phase is larger than that of the solid, which results in higher entropy. There are many millions of ways those 24 students can be positioned in the lab at any moment. Particles in a liquid phase are similar. When a system goes from a bound or constrained solid to a flowing and undulating liquid, entropy increases. Now let's imagine that class is over, and we dismiss and give those 24 students jetpacks. They can go in any direction in the sky. How many arrangements are there now? The number of ways those 24 students can be arranged in the sky is huge. This is like the gas phase, where particles are constantly in motion and can be anywhere in a three-dimensional space. Gases have so many more possible arrangements than liquids have, so a liquid to a gas phase transition makes omega increase by many orders of magnitude. When a solid changes to a liquid, entropy increases. When a liquid changes to a gas, entropy increases even more. So far, we have been talking about phase transitions, which are physical transformations. We can apply similar reasoning to chemical transformations. Let's look at the reaction that occurs between vinegar, aqueous acetic acid, and baking soda, sodium bicarbonate. We have an aqueous solution, which has intermediate entropy, and a solid, which has a pretty constrained and low entropy. As the reaction occurs, it makes an aqueous solution, a liquid, and a gas. And that gas has lots of freedom to disperse into lots of possible arrangements. Overall, the products have a greater freedom of motion than the reactants. So the entropy increases, and the change in entropy has a positive value. When ammonia gas and HCl gas react, they form a solid. Two gases have lots of freedom of motion, but the solid is tightly constrained. So the entropy decreases as these free-moving gaseous reactants form a constrained solid. Being able to predict when entropy increases or decreases is an important factor to consider when we're trying to predict if a reaction is likely to occur. So it's helpful to be able to look at a chemical reaction, analyze the possible arrangements of the reactants and products, and know if the entropy is increasing or decreasing. We can often look at a process and determine whether entropy will increase or decrease. When our sandcastle falls apart, entropy certainly increases. Knowing whether entropy drives or doesn't drive a reaction helps chemists predict the behavior of chemical processes and unlocks the secrets of how our universe works.